Там запись очень много, да. Себе. I will just like 5 minutes or something explain what we can do or branching out for context of it. And then we will go to yeah, it's on YouTube, so yeah. But let's do it quickly and then we'll go to manual exercises. Yeah. Well, there is no one online, so I think they fall asleep. I mean, if you're in close to the teacher, you're too scared to fall asleep.
No, it just doesn't work like that. I used to fall asleep on the first desk lecture. Evgeny Vladimirovich Dashkov remembers. Nie, on вообще спокойно не общались.
You know, Евгений Дашков. Just on the same boat with him there.
But be careful. I not got the first part anyway. Okay.
No, we all laughed.
We are the lost generation. The last ones who studied software engineering while it was
Okay.
study
History of Russia.
history of Russian.
Oh,
I think there are some positives.
Yeah, of course, of course.
The Java course was upgraded software construction.
but 20 years ago, I had to learn Java. I never used it in my life. Just C++, I should know. I regret not learning because I wanted to make grader in C++ for you.
Now they study like assembly language, C, algorithms, and data structures, and mathematical analysis, and all this stuff. Now, it kind of seems better.
But you didn't have algorithms though.
Yeah, it was kind of screwed up because they had to change the professor in the midst of the year.
Yeah, a lot of things. Yeah.
Also, I think for the first month it didn't start.
The guy just
Because
didn't
they-
come to the lectures.
No, they were trying to find the algorithms teacher.
But it's easy to find algorithms teacher. Should be easy.
For
There's
some
so
reason,
many of
Or maybe
people.
maybe it was not about.
Yeah.
By the way, which language do you use?
I
So which
English.
programming language?
Yeah. No.
Program in English.
So Python I can program. So yeah, I wrote a grader in Python because it just for mathematical research. I don't need
So
complicated
it's
things. Yeah.
enough.
Yeah.
Python, because it's the best language in the world, actually. The Python was value semantics, so it would be the best language.
Better semantics.
Value semantics.
Value.
The Python uses reference semantics by default. If you know,
For immutable.
immutable objects.
Yeah.
Yeah, of course, for primitives, it's value semantics
Yeah.
still, but for mutable objects, when if there was a version of Python with value semantics for them,
Yeah.
it will be instantly the best language in the world.
But it will be even slower, I think. If each time you have to copy all these lists, how can it work at reasonable speed?
So then they have pointers, semantics, and they get Golang or something like that.
C++, so we use value semantics.
Yeah.
You could pass pointer.
Yes, and you can do the same in Python. you could have короче, you could have done the same.
Yeah, but copying this is easy, but to brackets and double point if you want values symmetric.
Yeah, I know.
I agree that's a lot of bugs because you like changed something somewhere
Yeah,
because
yeah,
you
yeah.
forgot. Yeah, okay, but we should work instead of talk. So just 5 or 10 minutes branching out. So what did we achieve? So we had we already said 2 to the k like n to the power c algorithm for vertex cover. And now we can put here 2 to the power k. But now let's take a little bit about this constant 2 here. So we can do better, which was the promise. And so there we will use 3 ideas. So the first idea we already mentioned. So for if we pick a node, here is a node of degree 3, and so here is more of the graph. Then we have 2 options. Either we put the node in the vertex cover, or if we believe the node is not in the vertex cover, then all its neighbors must be in the vertex cover. And so the first idea is when we branch, we select the node with maximal degree. Because then when we have a tree, we will have one branch will recurse with k minus 1, the other branch will recurse with k minus d. And so if we can guarantee that d equals 10 or something, then we know the second tree, the second branch will be 10 times 10 units shorter. But this happens recursively. So it will be exponentially thinner or tree. And we will get the better constant. So what we will achieve is 1.46 or something to the power k. And this is cool, it's almost square root 2. That means we get twice as big k we can deal than original thing. State of the art is 284 or something. I'm not sure about the last digit to the power k. So it means you can double another time. And it means that if k is up to 190, there is something like clamp value. It's not so serious, but it gives some idea like that's 10 to the power 20 operations. That's like the maximum the bus will pay for or something. At least already 30 years, they say that this is kind of, it's a 1 CPU year or so. Okay, I don't know, 5. So, and then if k equals to 190, you're still good. If you have less CPU time, then maybe k equals 170, but that's pretty big because we will see that the graph is at least twice the size. So if your inputs are a few hundreds, and then you can be lucky that there is extra structure and it's worst case time bound. Okay, but so this is the goal for now. And as I said, we will combine 3 ideas. So first idea is pick the node with largest degree. Second idea, if our graph only has nodes of degree 2, we can compute the answer in polynomial time. So why is it? So if we only have nodes of degree 2,
We want to check
what is minimal size of vertex cover?
the minimal.
Yeah, minimal size of vertex cover of degree 2. So how can we know it right away when all nodes have degree 2?
We should check that the graph is a circle.
Yeah, the cycle graph is a union of cycles and paths. And so for a cycle, it's easy to know the minimal size of vertex cover. So this is 5, 1, 2, 3, 4, 5. So what's the minimal size of vertex cover of the cycle? 3. Yeah. Yeah. So for cycle at all position, but unfortunately one is covered twice, so we cannot avoid it. So if there's an even cycle of even length, then it's precisely how we can use.
We can divide by 2 and round.
Yeah, yeah. But here is 8. then you select these in the vertex column, right? For cycle, the vertex column is half, and then for paths it's similar. We need to think, so if the length is even, then it's half of the length minus one. And then, okay, I don't need to explain, it's for you, maybe 29.
But what is if the graph is not a cycle?
Yeah, then it's a path. So if all degrees are at most 2, then there are vertices, might be vertices with degree 1. They are endpoints of a path.
The graph is either a cycle or a path or a combination.
No.
So we look to all connected components, and each connected component can only be a cycle or a path.
Yeah, you could have 2 cycles or
Yeah.
cycle and a path.
5 cycles on a
So
path.
you
Yeah.
could divide them.
Yeah, and then for each, you compute the, so then we're very happy if all nodes have degree 2. So that's good news, because if we take maximal, so this is a kernel rule, like reduction rule for kernel. We see all nodes have degree 2, perhaps we output the answer here. And otherwise, we have node of degree 3. And so this idea of selecting node with largest degree. So now let us bound the runtime and try to verify we indeed have this times poly f. Poly length number of nodes. Okay. So then we need to make a recursive relation because we have recursion too. So we start with argument k, and here we fix one node. Should I make an example, or it will be okay? Let's do an example. Okay, so no, that's 15 plus. Something like that. Okay, so we pick a node of degree 3, let's say this one. And then we put this one in the vertex cover. So we will have let's say we want the vertex cover of size 3.
It's not the largest degree. The largest degree.
It is here, yeah. Okay. Yeah, but okay, let's say algorithm is pick a node of degree 3, then I don't need to redraw of at least 3. So this is here. And so for k, let's choose, I think 3 will be enough, yeah. So and then we have this and one branch. And for the other, we add these 3. And after we add these 3, then we only have these 2 bottom left. So we have this thing and 0. Right? Because here we do -1, and here we do minus degree of the selected node. So we're
Well, what did we do now?
okay, so we are branching. And in the root, this is our instance in the mean. So this is the graph and the number 3. We pick a node, and then in one branch, we delete it, we put the node in the vertex cover. And here are all, this is what remains to be covered. And we used already one node, so here is a 2. And here we put the 3 neighbors in the vertex cover. So we decrease, okay, let's do 4, because otherwise here we already done. So then we will have 3 here, and we will have 1 here. And then we branch again. So we will pick a node of a degree at least 3. And then here we pick this node. So what's left is this and this. And 2. And on the other side, we pick the 3 neighbors. And what is left is nothing. The 3 neighbors cover everything, right? So we have empty. But there is a small problem. We subtract roots of -1. So this is a false one.
Why?
So we subtract, sorry, yeah, yeah, sorry, I'm wrong. We have 0. Okay, and here the same thing. So, okay, here are no nodes, sorry, here are no nodes of degree 3. So we apply our algorithm. So we decompose in parts and cycle. Here is just one part, and we know what node is enough. So here it's okay. So if we go in the recursion in this way, then we are actually maybe it's more clever to go in the small branch first. I don't know. Now I think about it in my solution of the programming exercise. I didn't think about doing it in this direction. Yeah, because this is a much smaller tree and it contains the correct answer. You might find it faster. Okay. So, but in the first case, we will go here and then see a path of length 4, which can be covered by 2 nodes. So this is the branching algorithm. And now we have to bound the runtime. And so note that here, each time we go to the right, the degree decreases by at least 3. At least, yeah. And so do you know how we can find a recursive relation for such unbalanced trees? Okay, then I will explain. So we will guess a power and then check that our guess works. So we need to think about the sizes of the trees. So, here we have a tree. So let us call S for size. A size with k nodes. Here we will have, we want to bound the size of a tree for the value k minus 1, here k minus 2. In the worst case, we have exactly 3 nodes each time. And so what we want to find, we want to find a recursive relation in which sk minus 1 plus sk minus 3
But
plus 1, because we count the number of recursive calls.
3 here is the maximum degree. Yes.
Yeah, so 3 is the degree of the node
The degree of
Yeah.
that node that is
that we pick, and we guaranteed. So we always pick a node of degree 3, and if there is no such node, we compute directly. So then we are in the deep of our tree.
all the nodes have more than 3.
Very good, and then we just pick any one of them.
Yeah.
Okay, so there are 2
is-
variables. So what's clever if you program is to pick a node of maximal degree. But now I explained that we just pick any node of degree at least 3 for clean proof, and because I didn't want to redraw this picture. Okay, so what we know is that maybe here we have smaller value. Sorry, I want to say, now we want to find the inequality as well. So we want to have upper bound on the number of recursive calls. So what's the number of recursive calls for a tree with k elements? It's the root plus the size of the 2 children. Okay, now we need to make a guess. And so we will say our guess is x to the power k. Sorry, first let us get to the rid of this plus 1. So I will define t equal to s. T of k is 1 more than 10, so 1 less than s of x. Sorry, 1 more than s of x. So then what we have here is t of k minus 1 is bigger than t of k minus 1 plus t of k minus 3 minus 2 plus 1. Okay, so you see why I changed from t to s? I want to bound S, but instead I will bound S plus 1. And if I do bound S plus 1, then it's nice because these -1 and -2 plus 1 falls off. Okay, now I can bound something like. So now we simply guess, we guess a function p of k equals to x to the power k. And then we will think, what is this x? So note that 2 to the power k will work. Okay, so what do we have here? 2 to the power k is bigger than 2 to the power k minus 1 plus 2 to the power k minus 2. But it's not a good upper bound, right? So someone is falling asleep. So yeah, it's almost finished, yeah. Okay, so but this is kind of a waste because we have a lot of it. If we divide by 2 to the power k, we just say 2 is equal to 1 plus 1/8 or something, 1/4. That's stupid. We should put a better one. So let's put x. And then we have x to the power k, x to the power k minus 1, k minus 3. And then we divide by x to the power k minus 3. So that will give us x to the power 3, x squared plus 1. So we want to find the smallest x for which this is true. And then we have the bound on the sides. And it turns out that's about 1.46. And so now we improved our algorithm and we can deal with k twice as large. So before it's probably like graphs with k 70, now 140 or something. Just to give you an idea. So, and that finishes branching algorithm. To go to state of the art, you need to do more things. It's really cool. I found some movie. But okay, first step is get rid of nodes of degree 2. So that's the task for the programming project. Just find the rewrite through where you get rid of nodes of degree 2. So find the reduction rule to cut out nodes of degree 2. And it's also an exercise now. Okay, so lecture is finished and we can speak about the exercises.
And the seminar part is not
Yeah. But it is streamed on how do I